Hi everyone, we're going to talk today about factoring algebraic expressions. Before we do that, we do have to review a few terms. The first term we want to remember is what is a factor? Well, a factor is just a number that divides evenly into another number. So if we were asking about the factors of 6, what are the factors of 6? Well, 1 goes into 6 evenly, 2 goes into 6 evenly, 3 goes into 6 evenly, 4 doesn't. If we divided 6 by 4, we'd have some sort of remainder, so we would say it doesn't divide evenly. 5 also doesn't, but 6 does. And so there we would have our factors of 6. If we wanted to talk about 10, we could see that 1 goes in, 2 goes in, 3 doesn't, 4 doesn't, 5 does. And in fact, we could go through 6 through 9 and test those out. None of those divide evenly. We would find that 10 is the next factor. The next term that we want to know is GCF. GCF stands for greatest common factor. And think about those words, the greatest common factor. So if we're looking at two numbers and we're trying to find the greatest common factor, we're going to look for the numbers that they share in common, and then we're going to find the greatest among those. So with 6 and 10, I see 1 as a shared factor. Those are common factors. I see 2 as a common factor. 3 goes into 6 but not into 10. 5 goes into 10 but not into 6. And actually 6 and 10 are not common factors either. So here, our greatest common factor, so if we asked ourselves, what is the greatest common factor of 6 and 10? Our greatest common factor would indeed be 2. That is the greatest common factor between those two numbers. One last term that we do want to refresh is, what does it mean for a number to be prime? To be prime, a number would be an integer greater than 1 with only 2 factors, specifically the number 1 and itself. Let's think of some examples. If we try to think of the factors of 7, let's see, 1 goes into 7, 2 doesn't, 3 doesn't, 4 doesn't, 5 doesn't, 6 doesn't, but 7 does. So in fact, here we see that 7 is what we would call prime, because the only 2 factors are 1 and itself. This is a set of very special numbers in math. Some of the other prime numbers that we work with are 3, think about 5, 11, 13, 17, and kind of the list goes on and on from there. But they're very special numbers because they can only be divided by themselves or 1 nicely without a remainder. So why are we reviewing all of this? Well, we want to look at some examples here of factoring algebraic expressions. Now let's take a look at 2x plus 2. This one doesn't look too bad, and in fact, at this point, we're able to say, well, hey, wait a minute, 2x is my variable term, and this positive 2 is my constant term. This looks pretty good. It's all simplified. Well, sometimes in math, we might want to unsimplify things. And this brings us to today's topic of factoring algebraic expressions. We can also think of this as undistributing. So we're going to take something that's simplified and put it back into a form where we have a factor outside of a parentheses and we have an algebraic expression inside. So let's see what's going on here. In this variable term, I have 2x. And what does that really mean? It means 2 times x. So we would call 2 a factor of this, and we would call x a factor of this. And what about 2? What are the factors of 2? Well, 1 times 2. Those are our factors. In fact, we could even think of a 1 over here as a factor, but oftentimes we don't really think about 1 because if we factor out 1, it doesn't really do anything to the equation, so we can kind of ignore those 1s. So what is the greatest common factor here? We have 2. 2 is our greatest common factor. So we take our greatest common factor and we put it outside of the parentheses, and then we think about what's left. If we were distributing that 2 in, well, the x by itself would have been there before. 2 distributed into x would have given us the 2x for a variable term. And then let's think about what would that 2 have been multiplying to give us the 2 in the constant term? Well, it would have been 1. And so in fact, we have this factored form of 2 times x plus 1. If you're ever questioning yourself and you're saying, hey, I want to check my work, I'm not really sure if I did this, we can distribute or redistribute. So we can do 2 times x for our first term, and then 2 times 1 for our second term, and we would actually find, hey, we did it right. Look at that. We got 2x plus 2. Awesome. Everything looks good there. Let's take a look at another example. We're going to look at 4x plus 12. I'll take a look at this one. Well, let's start looking at the factors. Well, 4, this 4 right here. Let's see, 4 has factors of 1, 2, 3 doesn't go into 4, but 4 does. That looks like we're good there. And 12 has 1. Let's see, if we divide by 2, we get 6, so that's good. If we divide by 3, we get 4. If we divide by 4, we get 3. 5 doesn't go into 12, but 6 does. Let's see, 7 doesn't, 8, 9, 10, 11, and 12. So there are our factors, and let's see which ones are in common. We've got 1. We've got 2. And we've got 4 as common factors. So in fact, we say, well, hey, look at that. That is our GCF, our greatest common factor. So let's take that out over here. We're going to take that greatest common factor and put it outside of the parentheses. Let's think about what would have had to have happened if the 4 was distributed in. Well, before, just an x would have been here, just one x, because 4 times x would have given us that 4x. And what about our constant term? What was here before? What was here before? 4 was distributed in to some number, and it became 12. Well, that seems like 3 to me. 4 times 3 would have gotten us our 12. So right there, that is our factored form. Very important term to put away in your brain. That's what we call our factored form. There are some other ways to look at these numbers. Some people like to do these lists out like this. Others like to think about what's called a factor tree. So we can think about the pairs of numbers that multiply to get to 4. Let's see, I can do 1 times 4, and I can do 2 times 2. For 12, I can do 1 times 12. I can do 2 times 6. I can do 3 times 4. And in fact, doing it this way, we'll also be able to see all of those common numbers. We see 1 in there, we see 2 in there, and we see 4 in there. This is another way to think about it. These are just using what we call factor pairs. There's actually one more way that some folks look at it. They do what's called a prime factorization. So they're going to take this number and strip it down to only prime numbers. They say, well, 4 is 2 times 2. Those are prime numbers, so I can't go any further. 12, let's see. 2 is a prime number that goes into 12, and it gets a 6. But 6 isn't a prime number. 6 is made up of 2 and 3. And there we go. Those are our prime numbers. And this process is a little bit different. We see we have 1 2 is shared by both of them, and another 2 is shared by both of them. So that would tell us that 2 times 2 equals 4, and 4 is our greatest common factor. So there's a bunch of different ways. You can think about factor pairs. You can think about your prime factorization. Or if you kind of have these numbers and how they break down in your head, I think this top method is the fastest. I think prime factorization is the most guaranteed way to make sure you're catching everything. So let's look at another example. All right, going a little quicker. Now we have 15x minus 21. We're going to look at those two numbers. We can look at them any way that we would like. Any way that we would like. You can do your lists, you can do your trees, however you would like. You can set it up however you want, as long as we are trying to find that greatest common factor. So let's see. I see 15. I know that I can fit 5 into 15. And if I divide 15 by 5, I get 3. And well, both of those are prime numbers, so I might stop. I'm going to use the prime factorization method here. 21, let's see, I know that 3 and 7 go into 21, and actually both of those are prime numbers. So I can't go any further. There's no more numbers that I can divide 3 by other than itself and 1. Same thing with 5 and 7. And so let's see what's common here. Looks like we got 3 goes into each of them once. So we would say our greatest common factor is 3. I'm going to come over to this problem. We're going to put our greatest common factor outside, and we're going to think about what was there before. What was there before? Another way to think about this is we can take this number here and divide by 3. And if we take 15 divided by 3, we would find that we would have had 5x before. We divide that greatest common factor out because if we distribute it in, we're multiplying. So again, we're dealing with this idea of opposite operations or inverse operations. And then let's think about this 21. This 21, if we divide that by 3, we get 7. And that checks out because 3 times 7 is 21. The tricky part here is just always, always, always be careful about your signs. We have a positive 3 out here, so we have to have a negative 7 in here to get negative 21. So our final factored form would look like this: 3 times 5x minus 7. Awesome. Okay, let's do another example. We're going to look at 24x plus 30. Slightly bigger numbers, but not that bad. So let's do our factorization. And actually, I'm going to do it 2 different ways to kind of show you some options. Let's take a look at 24. This is where number sense starts to come in for this method, when we're just kind of listing out the things that we know go into it. I know 1, 2, 3, 4, 6, 8, 12, and 24. Now, if you don't memorize all of those, if you don't have all those possibilities memorized, if you didn't know that all those numbers go into 24, this method might break down a little bit for you. Let's take a look at 30. Let's say 1, 2, 3, 5, 6, 10, 15, and 30. Those are all of the factors of 30. And in fact, if we do this out, we can kind of start to see, let's see, 1 is shared, 2 is shared, 3 is shared. I don't see 4 or 5 shared, but 6 is. 6 is definitely shared. And that seems to be our greatest common factor. Before we go back, I do want us to just see this other method of prime factorization. It's a much more explicit way of getting what you want. Maybe you don't know that all of those factors go in, but you know that, well, hey, I know 2 is a prime number that goes into that, and 24 divided by 2 would get me 12. Here we have a prime number. We're happy with that, but 12 is not, so we got to keep going. What goes into 12? Well, let's see. I could do 2 times 6. I know that that's how I can get there, and 2 is a prime number, so I can stop there. But 6 isn't, so I got to keep going. Goes into 6, 2, and 3. Well, look, there we go. There's 2 more prime numbers. There are our prime factors. Do the same thing with 30. Right off the bat, I see 30 and 10. Those are the ones that jump out at me. So there's 3. What about 10? 10, I know 2 and 5 get us to 10. And in fact, both of those are prime as well. The only extra step with prime factorization, which does make it a little bit more work than just listing out the factors, is that now we have to figure out how many times these share some prime numbers. So it shares a 2 and it shares a 3. So we'd actually have 2 times 3, both as common factors. And so we find here that, well, hey, look at that, 6 is our greatest common factor. So we can get there using both methods. Really depends on how we visually see it. But the process is the same once we come back over here. We take our greatest common factor, we put it outside, and we think about what had to have been there before we distributed. We can also do 24 divided by 6, which we find out is 4x. Same thing with 30. We know that 5 would have had to have been there, and it was a positive. Again, if you ever wanted to check, you could do your 6 times 4 and your 6 times 5. You could kind of redistribute and see if you get back there. But here is our factored form, 6 times 4x plus 5. And you should notice also that the numbers in here no longer have any common factors. Let's look at another example. 3x plus 7. Do the same exact process. So we're going to come over here and look at 3, and we're going to look at 7. Let's see what goes into 3. 1 does, 2 doesn't, and 3 does. So those are our factors. It's a pretty short list. In fact, we notice, well, hey, this is prime. This is a prime number. What about 7? 7, 1 goes into it. 2, 3, 4, 5, and 6 do not. You could test it out, but they don't. 7 is the next one, and well, hey, wait a minute. This is a prime number as well. And so we see here a situation where there is actually no greatest common factor. Yes, they share 1, but we don't factor 1 out because it just leaves us with what we had before. So in fact, we wouldn't even come over here. We're not able to kind of do our parentheses and kind of put all of our stuff in those spots. We're not able to do that. We would just say, if we were given this problem, we would say, this is prime. We'd say this is already prime. That's our answer. Basically saying we cannot factor this one. And this can happen in one other situation as well. Let's take a look at 6x plus 35. We might be encouraged because we see, well, wait a minute, 6 and 35, those aren't prime. So let's do this one out. Let's see, 6, we have factors of 1, 2, 3, and 6. And let's look at 35. 35 has 1, 5, 7, and 35. Well, wait a minute. Something happened here. We definitely share 1, but I don't see 2 or 3 or 6 on the other list. I don't see 5, 7, or 35 on the other list. So in fact, here we also have a situation where there's no greatest common factor. And we would also call this one over here, we would say, hey, this is prime. There's no factor, no greatest common factor that we can pull out. And that is everything I have for you. You should have some practice problems. Give those a try, and I will see you next class.